Good day, students. Myself, Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dongar College, Bikaner. I am dealing with the first paper, Classical Mechanics of MSc Previous. We were discussing motion under central force, and under this series, we have derived Kepler's first law of planetary motion. Kepler's first law of planetary motion states that orbits are conic section and they have center at one of the foci. And these conic section, they are elliptical for the case of planets. The equation of conic section is R is equal to P 1 plus epsilon cos theta. Here the factor P, this is L square upon mk, and epsilon is another constant, it is u dash L square upon mk. Now from this Kepler first law, we are going to derive the properties of conic section. That means I am going to derive that what should be the value of epsilon so as to decide the shape of conic section, whether it be elliptical, hyperbola or circular. The shape of conic section depend on the parameter epsilon. So in order to explore the shape, I am solving this expression R equal to P 1 upon epsilon cos theta. I am changing the basis of description of polar coordinate with origin at focus. That means I am changing to Cartesian coordinate. In order to solve this, I have substituted x as r cos theta and y to be r sin theta. So my first equation, which is equation of conic section, is r plus r epsilon cos theta equal to p. Here r cos theta is x, so the expression comes out to be r plus epsilon x is equal to p. R will be p minus epsilon x. Now I am expressing in terms of xy. R is, from these two expressions, R is under root x square plus y square. So squaring, I get x square plus y square equal to p square plus epsilon square x square minus 2p epsilon x. Now I am collecting the terms which have a factor x square. This term, first term, and on the right hand side, this second term has a factor x square. So taking common x square, the expression become 1 minus epsilon square multiplied by x square plus 2p epsilon x plus y square equal to p square. So this is our second order differential equation. Now I am deriving the various cases for the shape of conic section. In the first case, I am taking a situation when epsilon is 1. So substituting in this expression, this is the general expression which will be further used depending on the value of epsilon to find the shape of orbital. So putting epsilon as 1, this factor will become 0. It will be 2px plus y square equal to p square. On solving this, I get y square to be minus 2px plus p square. This is the equation of parabola. So, if we have the condition of epsilon to be 1, then the shape of conic section will be parabolic. Now moving over to the second case in which epsilon is taken as less than 1. I am taking my general expression again. This general expression, second expression, can be expressed as x square dividing by 1 minus epsilon square, x square plus 2p epsilon x divided by 1 minus epsilon square plus y square upon 1 minus epsilon square equal to p square upon 1 minus epsilon square. To simplify it, I am adding and subtracting a term p square epsilon square upon 1 minus epsilon square whole square. Now, this equation can be simplified as, this is the term y square upon 1 minus epsilon square. This forms the whole square. So, my right hand side, here I have two terms. This is the factor p square epsilon square 1 minus epsilon square whole square plus this was the factor on the right side p square upon 1 minus epsilon square. In order to simplify the right hand side, I have taken common p square upon 1 minus epsilon square. So, my expression takes this form. In order to make it more simplified, in a simplified view, I am substituting a as p upon 1 minus epsilon square and b as p upon under root 1 minus epsilon square. So from this we can see that the relation between a and b is a multiplied by 1 minus epsilon square. These are the semi-major and semi-minor axes. So my expression will be x plus x0 upon a square, this is a square, plus y square upon b square equal to 1. A and b are semi-major and semi-minor axes of ellipse. As we can see that this is an equation of ellipse. So the condition epsilon less than 1 corresponds to the case of a conic section, that is ellipse. Now I am moving over to the third case in which if we take epsilon to be 0, then our general expression was, this was our general expression. Here we have taken epsilon to be 0. These terms become x square, this is 0, x square plus y square will be equal to p square. We know that this is the well-known familiar equation of circle. So, epsilon equal to 0 corresponds to the equation of a circle. Now, the last case is when epsilon is greater than 1. This expression can be obtained from the general expression and using the case second in which we have epsilon less than 1 with a sign change of minus. Here instead of a to be p upon 1 minus epsilon square, we will have a dash to be p upon epsilon square minus 1. Similarly, for b dash we will have it to be equal to a dash under root epsilon square minus 1. And the equation will be x plus x0 dash upon a dash square minus y square upon b dash square equal to 1. And we know that this is an equation of hyperbola. So the situation in which epsilon will be greater than 1, our conic section will be hyperbolic in shape. Now, as we have derived the shape of our conic section, we will consider two type of forces, attractive, and the second case will be of repulsive. Attractive force, we know that it must be negative, and the equation of conic section is R equal to P upon 1 plus epsilon cos theta. The factors P and epsilon are: P is L square upon mk and epsilon is U dash L square upon mk. The attractive force, which is expressed by inverse square law, F is minus k upon R square. Since the attractive force is negative in nature, we must have this is negative only when k is positive. And since k is positive, k will be positive, so we will have p will be always be positive. Now, since p is positive, this p is positive, so for r to be positive, the expression numerator is positive. For whole factor to be positive, denominator must also be positive. That means 1 plus epsilon cos theta, this must be greater than 0. Here, what is the value of epsilon? Epsilon was r by d. This is a conic section which is defined as a curve for which the distance from a fixed point, this was the fixed point, and distance from this fixed point was r, to the distance from fixed line, the distance was small d. This ratio r by d, this is epsilon. Now, here we want that r must be greater than 0 and d is also positive. So, epsilon will always be greater than or equal to 0. For this is the condition for r to be positive. Now, here we have 1 plus epsilon cos theta to be greater than 0. From here, we can determine that the range in which cos theta must be confined. Cos theta will be, from this equation, it will be minus 1 upon epsilon, greater than or equal to minus 1 upon epsilon. And we know that cos theta can have a value in the range minus 1 to plus 1. So, we have from this attractive force condition, the lower limit of cos theta is minus 1 upon epsilon and the upper limit, as we are well familiar, is 1. So, since here epsilon we know that it will be always be greater than 0. That means epsilon will always be positive. And for cos theta to be confined between minus 1 to plus 1, epsilon can have value to be equal to 1 and it can also be less than 1. So, we know that what are these two conditions? We have already derived that epsilon equal to 1. This is the condition for parabolic orbit and epsilon less than 1. This is the condition for elliptical orbit. Hence, when we have attractive force, we can have both parabolic and elliptical orbits. Now, we are taking the case in which we have repulsive force. since we know that force is minus k by r square and the repulsive force is always positive. This F will be positive only when k is negative. So F will be positive. Now since P is L square upon mk, so P will be, K is less than 0, so P will be less than 0. Now from this condition we can say for R to be positive, 1 plus epsilon cos theta will be less than 0. Cos theta will be very much less than minus 1 upon epsilon. Hence, in this situation, epsilon cannot be equal to 1. So from here, in the repulsive case, parabolic and elliptical orbits are not possible. So we can have a situation in which epsilon will be greater than 1. That means only hyperbolic orbits are possible. So I hope you must be able to understand the shape of the shape of orbit under the condition of attractive and repulsive force, as well as the situation of epsilon, because it is the most important parameter that is the deciding factor to determine the shape of our conic section. Thank you students for watching.